Bismillahirrahmanirrahim and Assalamualaikum warahmatullahi wabarakatuh and a very good afternoon for everyone. My name is Muhammad Haikal Arif bin Rizwan, student ID MA24110 from the Faculty of Mechanical and Automotive Engineering Technology here at UMPSA. Today, I am privileged to present a comprehensive breakdown of a foundational operational methodology in modern engineering, the Six Sigma DMAIC framework. We will explore how this methodology acts as a data-driven engine to systematically dismantle process inefficiencies and engineer high-precision execution. To solve complex engineering problems, we cannot rely on guesswork or ad hoc adjustments. Instead, we deploy what we call the DMAIC engineering framework. Think of DMAIC as a cyclical closed-loop mechanism divided into five distinct operational phases. First, define, where we clearly state the problem and establish rigid project boundaries. Measure, where we collect empirical data to baseline the current process performance. Next is analyze, where we isolate data variables to identify and validate true root cause. Then improve, where we design, simulate, and pilot engineered solution to close performance gaps. And lastly, control, where we standardize protocols to lock in our optimization and sustain long-term gain. Every phase is a prerequisite for the next. Skipping a step compromises the statistical integrity of the entire project. Let us ground ourselves in the underlying theory. Six Sigma is fundamentally the mathematics of perfection. Our core philosophy is the relentless, uncompromising reduction of systemic variation within a process. When we look at the standard normal distribution curve, our mathematical objective is to pull the process distribution tightly around the mean represented by mu, ensuring that the nearest specification limit is at least 6 standard deviations or 6 sigma away. Statistically, our target is a maximum of 3.4 defects per million opportunities or DPMO. When an engineering process achieves this level of control, the results in an astonishing 99.999966% defect-free execution rate. In high-volume manufacturing or safety-critical engineering, this level of precision is what separates operational excellence from catastrophic failure. Before detailing the phases, let's address why organizations invest heavily in this architecture. The core benefit of DMAIC break down into three distinct pillars. First, structural problem solving. It completely eliminates operational guesswork. By providing a highly standardized roadmap, engineering teams remain aligned and focused throughout the project lifecycle. Second, data-driven decisions. DMAIC truly replaces human intuition, gut feeling, and historical bias with hard empirical metrics. We do not guess what the root causes are. We validate them statistically. And lastly, maximum efficiency. By identifying and aggressively cutting structural waste and cycle times, we drive productivity up while bringing operational costs down. Now, let us dive into phase 1, define. The primary goal of this phase is to establish our formal contract for improvement, the project charter. To build an effective charter, an engineer must answer four critical elements. First, the problem statement. We must define exactly what is broken, ensuring that the operational pain is fully quantified. We do not say the line is low. We state exactly how much yield or time is being lost. Second, the goal statement. This outlines our measurable end state. It defines the specific realistic target we intend to achieve by the end of the project timeline. Third, the business case. This answers the question, why act now? It explicitly outlines the financial or strategic impact of the project to secure leadership buy-in. And fourth, the scope. To prevent scope creep, we must explicitly declare what is strictly out of bound for our engineering team. Step 2 in the define phase is translating the voice of the customer or VOC into engineering terms. Customers rarely speak in technical specifications. A customer or line operator might give a subjective statement like, the machine is too slow and loud. As engineers, we cannot optimize a vague statement. We must perform an engineering translation to extract functional, measurable requirements known as critical to quality specs or CTQs. In this scenario, too slow and loud is statistically translated into clear binary metrics: cycle time of less than 4.5 seconds and a noise level restricted to under 65 decibels. Now, we have definitive targets to measure against. To close out the define phase, step 3 requires us to map the entire operational ecosystem using a high-level SIPOC diagram. This acronym stands for suppliers, inputs, process, outputs, and customers. We define who provide our raw materials, what precise inputs are required, the macro level process steps that transform those inputs, the resulting output, and finally, the internal or external customers who receive the final result. This macro map ensures that the project teams understand every single boundary and variable before a single tool is touched. We will now transition to the measure phase. Measure phase, where our focus shifts to quantifying the exact scale of problem. The golden rule here is simple. We must select key performance indicators or KPIs that directly impact our established CTQ specification. We split our measurement strategies into two distinct types of metric. First, leading indicators. These are our predictive metric. They drive future performance and act as early warning system. Examples include monitoring machine calibration frequency or tracking proactive maintenance hour. Second, lagging indicators. These are historical metrics. They measure past outcomes and show us the final result of our process, such as total daily defects or final yield percentage. By balancing both indicators, we get a transparent view of the process health. Step 2 of the measure phase is defining our data collection and sampling strategy. We cannot simply gather data haphazardly. First, we must design a sampling plan that selects a statistically valid sample size to represent the entire population accurately. Second, we enforce random selection to completely eliminate operator or shift bias during data gathering. Finally, we protect data integrity. Before we trust any dataset, we must run a gauge repeatability and reproducibility study or gauge RNR to mathematically prove that our measurement tools and operators are calibrated and reliable. Step 3 is establishing our statistical baseline. This creates a clear baseline yield of our current state, which allow us to accurately map the opportunity and distance to our future target. To achieve this, we calculate process capability expressed through the statistical indices CP and CPK. These indices measure the mathematical ability of our current unaltered process to consistently meet customer specification. If our gauge R&R prove our measurement system is sound, a low CPK signals that the process itself is highly incapable and requires immediate re-engineering. Once we have clean data, we enter phase 3, analysis. Step 1 centers on isolating systemic waste by categorizing every action into two categories. First is value added, or VA. These are steps that transform raw materials into final product action the customer is genuinely willing to pay for, such as precise machining or structural assembly. Second is non-value added, or NVA. These are the operational red zones, such as process bottleneck, excessive transit times, long material queuing, and costly product rework. Our core objective in this phase is to ruthlessly eliminate these NVA red zones to collapse our total process cycle time. Step 2 implements our root cause diagnosis mechanisms. We begin by brainstorming and structuring potential causes using the 4M's metric via a fishbone diagram, segregating variables under man, material, machine, and method. Once the potential failure points are categorized, we execute the 5 whys technique. We drill past superficial system by asking why at least 5 consecutive times. This discipline forces the engineering team to bypass superficial problem and unearth the deep core systemic failure hidden at the root of the defect. Step 3 is validating what we call the vital few. To do this, we visualize our data using the Pareto principle, commonly known as the 80 per 20 rule. This mathematical principle states that roughly 80% of the process defect originate from just 20% of the underlying root cause. Through strict data validation, we ensure we never guess. We prioritize and attack the highest frequency bars on our Pareto chart first. This systematic approach allows us to focus our limited resources on the root cause that yield the maximum engineering ROI. With validated root cause, we enter phase 4, improve. Step 1 focuses on solution engineering. We map out brainstorm solution onto a impact effort matrix, isolating our green target zone, which represent high impact, low effort implementation. Simultaneously, we prioritize karaoke or mistake proving mechanism. The goal here is to design the physical process or tooling so that human errors become physically impossible to make. A classic everyday example of Pokayake is an asymmetrical connector that can only be plugged in one specific way, completely neutralizing potential user error before it occurs. Step 2 is structured risk mitigation, executed in 3 rigorous steps. Step 1 is simulation. Before spending capital, we test theoretical solution in a safe, offline, or digital sandbox environment. Step 2 is the pilot run. We implement our refined solution on a small, live, highly controlled scale. During this run, we actively monitor the system for any unintended downstream consequence. Step 3 is full deployment. We execute a full-scale rollout across all lines only after we have compiled statistical validation from our pilot run. And now, our final phase, is control. We entirely dedicated this final phase to sustaining our engineered precision over time. To prevent the process from degrading back to its old habits, we implement real-time monitoring of process stability using statistical process control charts, mapping data points between mathematically calculated upper control limit or UCL and lower control limit or LCL. To lock this in, we formalize standard operating procedure or SOPs to physically document the new baseline. And finally, we embed response plan. These are pre-engineered automated action triggered immediately if a data point drifts toward a limit, catching variation before a defect is ever generated. And with that, we move to our summary. To summarize, the DMAIC framework acts as the definitive engine of continuous improvement through three distinct core tenets. First, data over opinion. Every single phase mandates rigorous statistical proof, successfully eliminating guesswork and cognitive bias. Second, customer centric. Every engineering modification tracks directly back to fulfilling the verified voice of the customer. And the third, cultural shift. Six Sigma is never treated as a temporary one-off project. It serves as a permanent, evolving operational baseline for excellence. Thank you, Shukriya, merci to all of my audience. If you have any question, just leave it in the comment section. And lastly, don't forget to like, comment, and subscribe.